the idea of this small presentation is just to show you the soil moisture water balance model, which we are developing here. So to show you some of the structure and some of the equations, just to give you some idea and raise some discussion based on that. So so if we wanted to represent, let's say, a catchment or a river basin in a model, then we have a land cover, we may have surface water storage, we have a surface water outlet from the river basin, and we have the unsaturated zone and saturated zone. The unsaturated zone mostly is considered at the root zone of the vegetation, and the saturated zone is the groundwater storage. And what we have from the water balance equation, we have precipitation and inflow coming into the river basin as input, and evapotranspiration and outflow as an outflow from the river basin. And this should be balanced with the change in the storage in the catchment or in the river basin. And the outlet from the river basin can include these three types of outflows. One is the surface outflow, the outflow from the river basin in the form of groundwater, and any artificial intake or outlet withdrawal of water from the river basin to other destinations. And the inflow also, we can have surface water inflow to the river basin. We can have inflow in the form of groundwater, and if there is any artificial water we bring into the river basin, such as from desalination and so on, that's included in the input. And naturally, we have precipitation as input and evapotranspiration as outflow or output from the basin. And in water accounting, if you remember in the OCW course, we have 4 types of land use categories in water accounting plus, and also the change in storage. So the evapotranspiration, the actual evapotranspiration, is the sum of the evapotranspiration from the 4 types of the land use cover, which also should be equal to the sum of the blue and the green component of the evapotranspiration. This is just to show for the within the catchment, we can create a grid representing all these processes. And if we take out that pixel or grid, the variables which we have as input and we need to compute are shown here. We have precipitation and evapotranspiration. We have surface runoff from the pixel, and we have a base flow component which is coming from the groundwater, and the surface runoff plus the base flow will give us the total runoff from the river basin. evapotranspiration, we have the blue and the green component, and to satisfy the blue component, we have supply to the cell. And we have also percolation from the soil moisture to the groundwater. And it's not shown here, but from the groundwater, we can have also deep percolation, which will be running out of the groundwater storage. So for the modeling purpose, what we know or what we have is precipitation, actual evapotranspiration, the land cover type. We can also know the reference evapotranspiration, the saturation content of the soil moisture. We can have the interception, and we can calculate also from the precipitation data the number of rain days. And the output, or what we wanted to compute, is the blue and the green components of evapotranspiration. How much supply is needed to satisfy the blue component of the evapotranspiration, and compute the surface run of the percolation, the base flow, and then finally the total runoff or the total outflow from the river basin. And yeah, we know these are the parameters. So the inputs we know, these are the items we want to compute using the model, and the model have some input or parameters which are based on land cover class, such as the depths of the root zone. For different vegetation types, the root zones are different, so we need to know the root zone depths. We need to know the retention capacity also, which is based on the land cover class, and we need to know the consumed fraction, or we need to assume the consumed fraction. This consumed fraction is representing, like, if we supply water to, let's say, as irrigation, maybe not all of the water which we supply is consumed through evapotranspiration. Some will be lost to runoff or percolation. So to represent that, we need to assume consumed fraction, which is usually less than 1. So the model which we developed here is based on the dynamic water balance model developed by Zhang and his colleagues. And the catchment in their conceptualization is treated as a system of two storages, the root zone storage and the groundwater storage. We have precipitation as an input, evapotranspiration as an output, and surface runoff, and we have percolation from the root zone to recharge the groundwater storage, and the groundwater storage will be drained through a base flow and deep percolation to deep layers of groundwater. This is how they schematize the model. And to look at the equations, for example, for runoff, they start the precipitation is the sum of the surface runoff and a catchment rainfall retention, which is X in this case. So this catchment rainfall retention is the amount of water which satisfies the evapotranspiration, which satisfies the change in the storage between the current time and the previous time step, and which satisfies also the percolation to the groundwater storage. And this model is based on a limiting principle to say that, okay, this XT, or the catchment rainfall retention, has a demand and supply limit. The demand limit will be the change in storage between the maximum soil moisture capacity and the current soil moisture capacity plus the evapotranspiration, the reference evapotranspiration. That is the demand limit for the catchment retention, rainfall retention. And the supply limit is, of course, the precipitation. So following an approach the same as the Bodico curve, what they say is the ratio between the catchment retention, rainfall retention, and precipitation will approach 1 as the demand limit by precipitation approach to becomes very large. That is in a very dry condition. The ratio between the catchment retention and precipitation will be close to 1. And the catchment retention will be close to the demand limit in a very wet condition, or the ratio between the demand limit and the precipitation approach to 0. So this relationship is represented using this graph. Here you can see the partitioning of precipitation into catchment, rainfall retention, XCT, and the surface runoff. So this is representing the ratio between the surface runoff and the precipitation, and the lower part representing the ratio of the retention, rainfall, catchment rainfall retention to precipitation. And this curve, the curve which we see in this graph, is represented using an equation which is as shown here. So based on that, if we calculate that F, then we can calculate the amount of exit, the retention, catchment retention, which is the product of the precipitation times this F. And this F is a function of the ratio of the demand limit by precipitation and a parameter called alpha. Alpha is the catchment retention efficiency, which we can easily relate with the land cover type. And from this, we can calculate the surface runoff as the product of precipitation times the difference of 1 minus this factor F. And similarly, water availability, they compute water availability as the amount of water available at the surface of the catchment, which is the sum of the retention amount and the soil moisture existing before, or the soil moisture at the time earlier. So this retention water availability also can be calculated as the sum of evapotranspiration plus soil moisture plus percolation. So using the same approach, they come up with, okay, what are the evapotranspiration opportunity, or the kind of the limit for evapotranspiration, which is represented as white here, is the sum of the evapotranspiration demand at that time and the soil moisture. So if we substitute, for example, this YT in the water availability equation, we can get that this equation, the water availability will be the evapotranspiration opportunity plus the percolation. So what are the limits for this? The limit for evapotranspiration opportunity is, the evapotranspiration, the maximum evapotranspiration is equal to the reference evapotranspiration plus the maximum soil moisture capacity. So also, again, using similar limiting principle, as the ratio of the evapotranspiration opportunity by the water availability is close to, will be close to 1, as the limit of the evapotranspiration opportunity by the water availability is very large. So that is in a very dry condition. And the limit for evapotranspiration opportunity will be equal to the maximum evapotranspiration opportunity as the ratio between this limit of evapotranspiration to water availability is close to zero. That is representing very wet condition. So this also is explained in this graph. So the broken lines indicate the limits, the supply and the demand limit, and the different arrows here you see represent the evapotranspiration opportunity, the soil moisture, and the percolation. So again, using the same principle, we can calculate the evapotranspiration opportunity from the water availability, which will be the water availability times the F, which is a function of the limit of the evapotranspiration to water availability, and the parameter which I indicated here as a beta. And beta is evapotranspiration efficiency. In their model, because they don't know the evapotranspiration, they compute evapotranspiration, and then they compute this evapotranspiration efficiency. But for us, because we use evapotranspiration data directly from ET remote, which is the ratio of the actual evapotranspiration to the potential or reference evapotranspiration. Then once we know these parameters, we can easily compute the soil moisture, temporary value of soil moisture, which will be YT minus the actual evapotranspiration in this case. So here, this soil moisture computed here can be less than zero. That means it doesn't mean that the soil moisture will be negative, but it indicates that there is a need to bring in some additional water to satisfy this equation, or to make the soil moisture not negative. So that indicates the blue component of the evapotranspiration. And the base flow is computed simply as a linear function of groundwater storage, which is some parameter multiplied by the groundwater storage. And the groundwater storage will be updated by the previous groundwater minus the base flow plus the recharge of the percolation. Now, when we come to ET incremental, I said ET incremental is equal to the soil moisture when the soil moisture, the temporary soil moisture we computed above is less than zero. Otherwise, the ET incremental will be zero. And the blue, the green component, or ET rainfall, we call it sometimes, will be the difference between the actual evapotranspiration and the blue component of the evapotranspiration. And when the soil moisture is less than zero, that means when we have blue component of evapotranspiration, we need a supply of water to satisfy that. And we can compute that supply, Q supply, as the ratio of the blue component of evapotranspiration divided by the consumed fraction. And then when we know the Q supply, the soil moisture can be updated, which would be the soil moisture which we computed previously plus the supply. And finally, deep percolation can be computed as a function of the groundwater, which is multiplied with some parameter. So in this model, we have three parameters. One is the parameter to compute the groundwater. So it's using this linear function, the base flow. another is to drain the groundwater, and sometimes let me go to, the alpha, which is the catchment retention efficiency, which we can relate with land cover, but this retention parameter also depends on some other factors, like the weather condition, the antecedent moisture, soil moisture condition, the slope, the soil type. So we included a parameter also to adjust this catchment retention parameter. So we have 3 parameters for this model. And if you are interested to know more about this, the dynamic water balance model, which we use to develop the soil moisture awareness model, here you can read their paper. Here is the reference. They explained it in a bit more detail. And finally, to show you the effect of the retention parameter here, for as alpha is low, that means the curve will be very far from the supply and the demand limit, and as alpha increases, then the curve become close to the demand, the supply and the demand limits. So I understand this is a bit more going into the equations, a bit more technical, but we thought it would be nice to have some feeling of how we compute or how we model the soil moisture balance and some of the parameters, the values we use in water accounting. So if you have questions, comments, you are welcome to ask. Sheriff, you are asking something. Can you take the microphone and ask your question?
Yes, hello. Yes, actually, I was asking about the equations of the Q in and the Q out at the sum of the Q's in the first slide, I think, because I can see the minus equation, so I want to be sure that's
Where is in this slide?
the previous one.
First one.
The first one, yeah.
This one?
The first one.
I don't have any question on the first slide.
The second, please. The next.
This one?
The next. The equations.
Next
the equations.
Yeah,
yes,
this one.
This one.
Okay. Yes.
Yeah. The Qn is a summation, or it's Qn equals.
It should be plus, right?
Yeah, it should be plus. You're
yes.
right.
Yes. And the Q out also, and the Q out. Yes. Thank you.
Yeah.
Thank you.
Yeah. I don't know why they become minus. Thank you for spotting that. Okay. Other questions?
Lauren is asking if we can upload I think the PDF perhaps of these presentations, so that if people want to compare
Yes.
what they read in the Python file.
I will upload it right away. I forgot to upload it.